You probably know many different types of energy. For example, kinetic, potential, electric, nuclear, and more. If we take all of these types of energy in a system, the sum of that is called total energy, and it's represented with a capital letter E. If we were to represent this on a unit mass basis, then we use a simple letter E and we can write it like this. All we're saying is that on a unit mass basis, our total energy is simply the total energy divided by the mass. So our units would be joules per kilogram. But most of the time, you will have it as kilojoules per kilogram. In simple terms, it's energy per kilogram. You should be familiar with kinetic and potential energy. Kinetic energy is half times mass times velocity squared. Again, if you need to represent this on a unit mass basis, you divide it by mass, so you end up with half velocity squared. In simple terms, it's kinetic energy per kilogram. We do this because sometimes we need to figure out the energy per unit mass basis. You will see how this becomes helpful when we do examples. Potential energy is mass times the acceleration due to gravity times height. On a unit mass basis, we divide it by mass, so we get just the acceleration due to gravity times height. The units are the same as kinetic energy, so kilojoules per kilogram. The total energy of a system can then be represented with this equation when we consider kinetic and potential energy. Here, the letter U represents energy relating to the molecular structure of a system. In other words, internal energy of a system. If we write this on a unit mass basis, we just use simple letters. Potential energy and kinetic energy are extensively covered in the dynamics video playlist, and because of that, we will not dive deep into those topics. Rather, we're going to look at something new called mass flow. When we have open systems, also called control volume, it involves mass flow. So air going through a duct or water going through a pipe, things like that. Sometimes, we need to be able to see how mass is flowing through a section with respect to time. We call that mass flow, and that's the amount of mass flowing through a cross-section per unit time. It's represented with the letter M with a dot on top, also called m dot. You might have seen this dot before, and it simply represents time rate. In other words, something that happens per time. So here, it's how much mass is flowing per second, and the units would be kilograms per second. In simple terms, how many kilograms of mass is flowing per second? This mass flow rate is also related to volume flow rate. That's the fancy letter V with a dot on top. That would have the units of cubic meters per second. So in simple terms, how much volume is flowing per second? We can relate them using this equation. Here, rho is the fluid density. It's also equal to this. The letter A represents the cross-sectional area of flow, and V average is the average flow velocity. Another way we can relate them would be like this. Here, it's the volume flow rate divided by the specific volume. Hopefully, you remember that specific volume is volume divided by mass. So this is just isolated for mass. Now if we wanted to find the energy flow rate with the fluid that flows, then we can find it using this equation. The units would be kilojoules per second or kilowatts. So what we're saying is that the energy flow rate is equal to the mass flow rate multiplied by the total energy of a system on a unit mass basis. Sounds kind of complicated, but in simple terms, it's just how much mass is flowing per second multiplied by the total energy of a system. You might notice that this is pretty much the equation we talked about before, just rearranged and is written with respect to time rate, so with a dot on top. One last thing we need to talk about is mechanical energy. It's a form of energy that can be converted to mechanical work. But what we're interested in is how the pressure of a flowing fluid is connected to mechanical work. For example, when water goes through a turbine, what's happening is that the turbine extracts mechanical energy from the water by dropping its pressure. Pressure itself is not a form of energy, but if we look at a pressure force that acts on a fluid through a certain distance, then that creates work, and it's called flow work. Flow work can be expressed like this. So pressure multiplied by volume, which would have the units joules. We can also express it on a unit mass basis, so that would be pressure divided by density. The units for it would be joules per kilogram. If we were to combine everything we talked about, we can write it like this on a unit mass basis of the fluid. This is the flow energy, this is the kinetic energy, and this is the potential energy. If we wanted to write this in the rate form, we can do so like this. Remember that m dot is the mass flow rate of the fluid. Now let's move on to some examples to see how to apply what we learned. In this problem, we have a turbine 120 meters below the free surface of a water reservoir. The reservoir can supply water at a rate of 2,400 kilograms per second. We need to find the power generation potential. First, we write down what we know. The height is 120 meters, and we have our water rate as mass flow, so that's 2,400 kilograms per second. Lastly, the acceleration due to gravity is 9.81 meters per second squared. Our first goal is to figure out the mechanical energy. In this case, we know that water has potential energy because we have a height difference. We can figure it out per unit mass. We know that on a unit mass basis, potential energy is gravity times height. This is why we discuss per unit mass, since here, it's not possible to use a mass for the water. Let's plug in the values we know. Keep in mind that we know for potential energy per unit mass, our answer is supposed to have the units kilojoules per kilogram. So we need to use a unity conversion ratio. I'll break it down step by step. A joule is equal to kilogram meter squared per second squared. So that means joules divided by kilograms gives us meters squared over seconds squared. 1,000 joules is a kilojoule. Now that we have our answer in the units we want, let's move on to figuring out the power generation potential. In other words, the energy flow rate. Here, we need to use the given mass flow rate and the equation we talked about before. So this is the total energy we can get. Let's plug in our values, and here, I will write out the unity conversion onto the same equation. 1 kilowatt is equal to 1 kilojoule per second. All the units get cancelled out and we're left with just kilowatts, and that's our answer. If the units give you a hard time, you can always follow the process I did previously and break it into steps. In this question, we have buckets around a wheel. The water is sprayed from a nozzle at a speed of 60 meters per second and has a flow rate of 120 kilograms per second. We need to figure out the power generation potential. As always, we write down what we know. The velocity is 60 meters per second and the mass flow rate is 120 kilograms per second. So as before, we need to figure out the mechanical energy per unit mass. Here, we're given the velocity of the water, so we know it has to be kinetic energy. Again, keep in mind that this is per unit mass. Let's plug the velocity in, along with the unity conversion ratio. This is the same as before, we want our answer in kilojoules per kilogram. Next, we need to figure out the power generation potential, so we can write down our equation. Let's plug in what we know. We need another unity conversion ratio. Let's solve, and that's our answer. Let's take a look at one last example. Here, we have a river flowing towards the lake with an average velocity of 3 meters per second at a rate of 500 cubic meters per second. The difference in height between the river and the lake is 90 meters. We need to figure out the total mechanical energy of the river water per unit mass and the power generation potential. Notice that we're given a rate of 500 cubic meters per second, so that's volume dot, in other words, volume flow rate. We also have the velocity of the river water, which is 3 meters per second, and the height is 90 meters. So first, we need to calculate the total mechanical energy. That will be the kinetic energy of the water because we have velocity, plus the potential energy because we have height. As usual, we will write it per unit mass. Let's plug in our values and our unity conversion ratio. Let's solve, and that's our total mechanical energy. To find the power generation potential, we use this equation, which is the energy flow equation. So the same one we've been using before, but notice we don't have the mass flow. We need to figure that out. For that, we can use this equation. The density of water is 1,000 kilograms per cubic meter. Let's plug in our values and solve. This is our mass flow, so we can use this in our energy flow equation. Let's plug them in and solve, and those are our answers. That should cover the types of problems you will face when it comes to mass flow, energy flow, and more. I hope this video helped. Thanks for watching, and best of luck with your studies.